Merhaba. Hello.
Merhaba.
Merhaba. Ben bilemedim, kusura bakmayın, Türkçe ne kadar hatırlıyorsunuz, konuşuyorsunuz.
Yok canım. Tabii ki.
Ya bazı insanlarla röportaj yaptığımızda onlar hani biraz unutmuşlar, rahatsız oluyorlardı. Hani o yüzden öyle soruyorum da. Ben
Hani o tamamen Türkçe yapacaksınız sanırım, değil mi? İngilizce yapacaksınız
ha,
interview'u.
evet. Sadece en sonunda sorulardan Türkçe belki soranları ben yine İngilizce size söyleyebilirim de. Sizin için hiç fark etmez. Ben nasıl size sunum zaten İngilizce olacak. Onda bir sıkıntı yok.
Evet. Ya benim için fark etmez, Türkçe de yapabiliriz o kısmı.
Evet, ama yani normal anlatım kısmında zaten yabancı insanlar da bizi biraz takip ediyor. Onları da şey almaması için
Hı hı.
şey
Tabii
yapalım.
tabii. Nasıl? Genelde bir saat mi sürüyor? Onu da sorayım.
Genelde bir saat sürüyor. Sadece bir kere 2 saat sürmüştü. Çok fazla soru gelmişti o gün. Giriş ve nasıl bu alanda ilerlerimle ilgili biraz bir video şeydi ama bir saat genelde yeterli oluyor.
Okay. Ya, yani ben tam time etmedim prezentasyonu da, herhalde yarım saatte biter yani.
Tamam. Çok bizim de 10-15 dakika bir soru kısmımız olur sanırsam. Hem benim kendi hazırladığım sorular var bir gruptan aldığım. Bir de YouTube'da da chatten gelen sorular olur. Onları da yani ilginç veya çok böyle saçmalamayan arkadaşların sorularını alacağız. Tamam. YouTube'da şu an biz yayındayız sanırsam. Kontrol edeyim. Sıkıntı yoksa başlarız şimdi birazdan. Hande de bizim arkadaşımız gruptan. O da Zoom'da bize 3 kişi olacağız bugün.
Merhaba.
Evet.
Ben bir topluluğu ve bugünkü konuyu anlatayım, sonra da başlayalım, size bırakacağım tamamen. Hello all, and this is I can't remember which one of these, like, we don't count anymore, but this is like our fourth or fifth one, and we are now gonna interview the Ilge Akkaya. She works at the OpenAI, and she worked at the Cubic project with the OpenAI, and she also studied at the UCBerkeley and Bilkent University in the bachelor. And if you have questions, please write in the chat. We will try to ask them as many as possible in the end. And if you have like any problems with the video or sound, please let us know, because otherwise we can't detect it. For us, it looks okay, but we can't detect it beforehand. And Türkçe soracak sorularınız olursa da arkadaşlar sorabilirsiniz. Ben en sonda onları okuyacağım ya da Türkçe şekilde de yapacağız. Ilge, I'm letting you your presentation. Thank you for joining us today.
Yeah, thanks for inviting me. So let's do the screen sharing part first. I think you might have to enable something for me to be able to share.
Sorry. Can you try now?
Yeah, I think you should be able to see my slide now.
Yes, it's perfect, yes.
All right. So let's get started. Hello, everyone. My name is Ilge, and I'm a member of technical staff working at OpenAI robotics team. And today I'll be talking about our work that we published last year on solving the Rubik's Cube with a robot hand. So one of the problems we're tackling at OpenAI is developing algorithms to power general purpose robots of the future. That is, the robots that can operate in complex environments of the real world and carry out most tasks a human can do today. Today's industrial robots are still quite far away from this vision. Most consumer-based robots are either focusing on basic obstacle avoidance, like the robotic vacuums, self-driving cars, or the ones that do actually interact with their environments. They're either human-operated or they play back pre-recorded trajectories. So we want to take this a step further. And we wanted to focus on dexterity. And the goal of the project was to actually perform dexterous in-hand manipulation with a humanoid 5-fingered hand. This is an important problem because the human hand is a universal end effector, and it will be essential so that we can perform most dexterity tasks a human can do. Despite the importance of the problem, there has been little progress with such robots so far. This is partially because devising control policies for such a complicated robot is a daunting task. Classical control approaches are often not very good at dealing with such a dimensionality. So deep reinforcement learning becomes an ideal target here because of that. So the difficulty of the problem actually lies mostly in the dimensionality of the system, as I said. For example, the robot we chose, Shadow Dexter's hand, it has 24 joints and 20 of these joints are actuated. So you would have to come up with a control policy that is able to deal with all of this control space at once. And the task is especially hard in this case because we need to train policies which are going to work well on physical hardware. In particular, it means that they have to be able to deal with noisy and delayed sensor readings and partial observability. So in terms of the history of this project, in summer 2018, there was a publication by OpenAI, which was basically a learning dexterity project. And the task here was a block reorientation task. The goal state is given by a particular pose of a cube that has letters on each side. And the goal of the humanoid hand is to basically flip the cube around so that it can achieve the target pose. And the ultimate goal was to achieve 50 such consecutive successes. So from there, in the fall of 2019, we actually extended the task significantly to solve a fairly scrambled Rubik's Cube using one human-like robot hand. This is already pretty challenging for a human to do with one hand, and for a robot, it is just even more. So just to introduce the project's goals, we really wanted to test the limits of sim-to-real transfer, state estimation from vision, dexterity to manipulate Rubik's Cube, and build to end-to-end working system. But we really did not want to focus on learning to solve the Rubik's Cube symbolically, because that actually can be done separately and in advance. So our project was actually learning the manipulation task itself. So the approach actually that we follow is that deep reinforcement learning, obviously, which has shown to be very powerful in tasks like AlphaGo and Dota 2. One problem with deep RL though is that it actually requires a lot of data. And when you're working with a real robot, that becomes a problem. Training on physical robots is one option here, but they're really expensive to build, costly to maintain, and they're really slow to iterate on. And yeah, like in our case, it was also a scaling problem. So our approach here was that we wanted to follow a sim-to-real approach, train only in simulation, no real data at all, but then eventually make sure that the models that we come up with can transfer to the reality of the real world. So when we started the project, it's actually surprisingly easy to solve a prototype of the problem in simulation. Although it's virtually impossible to accurately simulate in-hand manipulation due to a high number of contacts that you have to simulate and the level of accuracy you have to achieve. But the problem, in principle, can be simplified and solved in simulation pretty fast. So from there on, when you actually do something with the robot hand, it is surprisingly hard. What is even happening? So the problem that eventually was left for us was to figure out the transfer problem. So this talk is also going to be mostly about the transfer problem here. So to talk about the technique a little bit, domain randomization is one way to close the reality gap in the transfer learning setting. And the basic idea here is that you learn to solve a particular problem under many perturbations of the environment you really care about. And then you try to yield a policy that is going to be robust enough that eventually can deal with your reality. So one of the first examples of domain randomization for robotics was the work of Sadeghi and Levine 4 years ago. They trained this policy for trying a drone in a simulation with lots of varied textures of the environment. And they showed that the drone can actually perform well when flying in the real world without being trained on a single real image. So very promising. This approach was also adapted at OpenAI. In 2017, the same approach was used to train a vision model to predict the object's position and orientation by randomizing the environments in a pretty unrealistic setting, but surprisingly, this also transfers to the real world. So these two were actually examples of domain randomization in visual domains, but then in 2018, there was an extension of this to physics randomization. So OpenAI actually also showed that instead of changing the textures of your visuals, now you can randomize parameters of your physics simulation so that you can come up with robust dynamics of the robot. So here you're seeing a comparison of the two policies, and the one on the left was trained with physics randomizations. The goal here is to push the puck to where the red dot is. And as you can see, the policy that does not have physics randomization, it is overshooting and failing to achieve the task. All right, so we decided that reinforcement learning plus domain randomization is a promising setting to solve something as complicated as Rubik's Cube. But in our case, we eventually need both visual domain randomization, physics domain randomization. And as you're working with such a high dimensional system, domain randomization really does not scale. So because of this, we had to extend the DR framework by coming up with an automatic domain randomization formalism. And here is how it works in a nutshell. So we start with a single environment initially that we care about, and we start training the RL task on this one environment. As we get enough performance out of the model, then what domain randomization would do would be to just extend the environment in a given manual set of randomizations. So we would now try to learn the task in this whole set. But what ADR does instead is that it is able to do this adaptively. So as you get better at the task, you can grow the set adaptively based on how well your policy is doing, and just keep going. The better the policy does, the more we can randomize in the environment, and this process can theoretically just go on forever. So ADR is something we use both in the vision domain and the policy domain. And the visual appearance of the cube and camera angles, for example, are some things that we randomize for the vision network. And for the manipulation part, we can just do many things like change the dynamics of the hand, mass and size of the cube. Many things can be randomized. The way it works is that we start off with an initial ADR distribution. We sample environments from this initial distribution, generate some data, just rollouts from the sampled environments. We optimize the model, evaluate performance of the new parameters under the new environments, and then we eventually go back and modify our distribution. So that means, as an example here in our project, we start off with a cube size that is corresponding to the real cube that we are planning to use in the physical experiments. For the first day, the policy, say, is not able to deal with any other cube size. It just doesn't know about the RL problem enough yet. And then once it gets better, we are able to expand the cube size to be smaller or larger than the actual cube, and eventually the policy will learn to generalize to that. So at the end of the day, we ended up with like 60-something manipulation parameters that we could randomize for the manipulation part alone, and that really helped solve the sim-to-real problem. All right, so let me explain how the end-to-end system ended up coming together. So as I talked about it, the ADR part is the most important part that allows us to generate very diverse data. So we use this data in two ways. We have a manipulation model, basically an RL policy that sees the cube state observations as well as the fingertip positions from the robotic hands, and uses an LSTM policy to provide actions to perform on the real robot. And on the vision side, it is seeing 3 randomized images, basically synthetic images from our simulator, just passing them through a connet and trying to predict the cube pose and face angles. So in case of the policy network, we were using proximal policy optimization to train this network, and we use separate value and policy towers for the task. Our observations were actually all embedded into a common space, so we can actually pretty flexibly add and remove observations. And as it is with PPO, we are only providing available inputs from the real robot to the policy network, but the value network can see some additional privileged information. And at the end of the day, what the action distribution ends up being is that it is an 11 by 20 distribution, where the 20 is the dimensionality of the actuator. So we learn a multi-categorical distribution for each actuator, and it is basically discretized, and actions correspond to relative actions. So basically, if the finger is at angle theta, we just tell it to rotate that particular joint by 10 degrees at a time. And for the vision state estimator, this is a supervised learning problem. The network is seeing 3 different cameras, each are passing through a resonance-based architecture, and eventually we are predicting the position, orientation of the cube, as well as face angles. Yeah, so to explain how this all comes together in sim-to-real, so obviously we now have 3 images from physical RGB cameras. They're passing through the learned vision network, which predicts pose for the cube and face angles. So in our case, we actually had 2 modalities. Because predicting face angles from images are very noisy, we also had the option to switch to an instrumented cube, which gave us Bluetooth-based readings of the actual face angles, sensed face angles from the cube. Actually, to go back to the vision alternative of this, because it's very difficult to tell the absolute rotation of a face of a cube from just a single static image, we had to use a trick to break the rotational symmetry in the images. That is, basically, we had to cut out the center sticker of the cube at each face so that you can tell by how much the face is actually rotated. Okay, so that path is either or. And then fingertip locations were being sensed from the physical robot, and this eventually all feeds into the policy network, and then we can use it on the physical domain. And yeah, so this is an example of our very cluttered cage where we have 3 RGB cameras and also a separate face-based tracking system, which is a motion tracking system that is very accurate, but we only use this for tracking the fingertip positions of the robot and nothing else. All right, so to talk about the results, this is really the end goal that we came up with. So you can see the LEDs on the fingers of the robot. That's how we're tracking the position. The cube in this case is an instrumented cube, but we're actually estimating the pose of the cube only from vision, and we're only at sometimes reading the face angles from Bluetooth. And just to jump to the interesting part a little bit, what we're doing in terms of goals is that the policy is told to either rotate a face or to flip a cube, and we just made it so to make it simpler that it can only rotate the top face. So it would, if it has to rotate another face, it would have to flip that face above and then make it be the top face and then rotate it. And so at the end of the day, after about 5 minutes in this case, the policy is able to solve the Rubik's Cube, and then we are going to be done. Right, so we also wanted to test the robustness of this a little bit. So these are just really things that the policy is not trained for. We wanted to tie the fingers together and see what happens, and just have some occlusion in the vision network to see if it immediately drops the cube or if something reasonable happens. And turns out the policy is robust enough that it can actually operate pretty reasonably under many different perturbations that it has never seen before. So in terms of some numerical results, we really want to show that ADR was the thing that made the difference here. So when we start off with a manual domain randomization, it is really a very narrow distribution of randomizations. And in that case, we're only able to make something like 2 mean successes on the cube. And as we make the ADR distribution wider and wider, we see that the successes also increase proportionally to that. And in the case that where we just basically wait for ADR to expand the longest, we were able to see the best results. And in that case, we can achieve something like 26.8 mean successes. So the top 4 results are all with the instrumented cube, but we also have a proof of concept where we're only relying on vision and no instrumentation in the object. That is the last row, where we can still achieve something like 12 mean successes. So it is clearly not as accurate as the face angles read from the instrumented cube, but it can be done. So to talk about the role of ADR also in simulation, there's this question of like, what if we did not use the ADR like we did, and to just provide a diverse enough set of environments from the beginning of the RL training? Would we have gotten the same benefit? And turns out ADR actually here already has a curriculum effect, so it is necessary. We see that the best learning curve in blue with ADR is actually able to learn the fastest in the beginning, but also if you look at where it ends up being at the end, so the horizontal lines are actually just the deterministic kind of hand-designed domain randomization, like I guess the preset domain randomization magnitudes, and you can see that it can achieve the level pink achieves at the end, only being better from the start. And the final thing to mention here is that we also observe some meta-learning properties from our experiments. So what that means is that here we are actually looking at how the policy learns to generalize as it identifies more about the system. And the experiment done here is that we're letting the policy in simulation to run for 60 steps and tracking how many seconds it takes to complete each goal. So in this case, so actually this is not 60 steps, it's just, we're just tracking how much time each goal takes to achieve. And we can see the first goal actually takes the longest. It takes a lot longer for it to achieve the first goal than to achieve the second one, and it just falls exponentially. And now we're asking the question, what if at time 10 and time 30, we randomly reset the hidden state of the policy? What is it going to be able to do? So as we see, if we do that, it actually jumps back up, which means that it has actually lost some information it has inferred about the environment. And then as it keeps going, it again learns to solve it efficiently. So it is about this meta-learning property that the policy is actually learning something about the diversity of the environment, and as you run it, it is able to infer what environment it is operating in. And a similar environment here is that you can just resample the environment dynamics in the middle of the experiment. And when you do that, it again has a similar effect to resetting the hidden state. It is first not quite sure what to do, but then able to identify what environment it's dealing with and solve the problem as efficiently as the baseline. And the final thing here is that another system identification effect that we see when we ask the policy to predict the cube size from the data it sees from the 6 simulation steps, we see that the more ADR randomizations it sees, the better it is able to achieve that task. So if you show it a lot more diverse information, the hidden network is able to capture a lot of your randomness so that it becomes a good predictor of all the parameters you have been randomizing. So yeah, these are some directions that are interesting in terms of meta-learning capabilities that just emerge out of using some randomization factor like ADR. With that, that's pretty much all I had. So if there are any questions, I'll be happy to answer them now.
Oh, yeah, I have a few already. And thank you for this good explanation. And there's some really good details. I think our viewers need to recheck this as a reference point for doing maybe something like automatic domain randomization. And one of the things that I had in the mind while you were talking about domain randomization was you obviously, I think all of you probably looked at but what was in my mind was did you think about applying something like a generative network to create some realistic data from the simulation, that approach?
So actually our simulation was pretty realistic. So there's this orb framework that has been also released that is based on Unity.
Yes.
So we are able to actually randomize textures and patterns. So it's pretty similar to the Sergey Levine paper from 2016 in that case. We're able to randomize all of the textures. It's not photorealistic, but we have shown that it shows good transfer to the real world. So we don't actually have to use generative networks in this case.
Okay. That was nice to understand. My second question was, did you explore possibility of using a depth camera for better understanding some position, rotation data maybe?
Yeah, that is a good question. We have later considered that actually, but there are a couple issues. Part of the issue is the availability of such depth cameras in the physical world. So we couldn't quite really find something at the time, and our setup was actually pretty reliable in terms of delivering frames super fast to us, which is always something very important. in such a network. So we actually went for a little bit of a simplicity in this case. So 3 RGB cameras were able to give us enough depth information, and we didn't have to go there. But yeah, so we have to again think about the availability of the hardware and the ease of simulation of that hardware to be able to train on that as well.
Yes, that's good to know. Relating to this presentation, I have one more, and other questions are more related to the generally reinforcement learning, if that's okay. We have, I think, a little bit time here. The question I had in the mind was like, this is, I think, still on policy training with the PPO algorithm. But what I had in the mind, I think the recent works, they show an increase in the something like batch mode reinforcement learning, or they now call the offline reinforcement learning. And do you think this approach could be useful here, that collecting a lot of data, maybe from the simulation, or already collected, maybe, I don't know about this domain, but maybe there are already collected data regarding to the cubic and the optimization of the cubic, solving cubes. So what I in the mind is the offline reinforcement learning with maybe labeled data or self-supervised data. Would it be useful in this case?
Yeah, I mean, I do agree that data efficiency, sample efficiency is an important factor. But in our case, so there are some trade-offs here. We wanted to go with PPO and the simple approach because it is tremendously stable, and you can apply something like ADR on top of it very easily. That's why that's the advantage of using the well-established method. You know that your simulation is going to be stable. You can keep randomizing your data. And also because we're using simulated data alone, honestly, it's not a super big problem that it's not the most sample efficient in this case. Yes. But yeah, definitely it can be improved. There are a couple things that help here. We have a separate vision network. So for example, we don't have to train that all the time. That is pretty static, and we only learn the RL part, and then we can combine the networks together. So that is, while you can also argue that end-to-end networks could be used, for example, that is an argument for why intermediate representation worked for us in this case. Mostly we're pushing for an end-to-end system that works. That's why sometimes you want to go with the more stable thing.
Oh, yes, thank you. You also already, by the way, answered one of my questions, because I was just going to ask what was the idea before for the separation, because one of the recent works that I saw was actually trying to show the grasping. It was for this grasping project, which was also trying to show power of the knowledge and improving the vision module, and they showed the results between a frozen vision module and between another model that was still training, also the vision model. And yeah, thank you for answering that. And the rest of the questions, I think, Hande, are you still there? Maybe you can ask your question.
Yeah. Thanks, Erkan. First of all, Dr. Akkaya, thank you for all the information you shared with us. So I think all of them were very valuable for us. So my question will be more a general one rather than a technical question about reinforcement learning. So I was wondering if there are people with backgrounds in cognitive neuroscience in your team or in OpenAI, or do you exclusively work with engineers?
Can you clarify the engineers part?
I was wondering if backgrounds with people with backgrounds exclusively in cognitive neuroscience, which who didn't have education as a traditional engineers or PhD and electrical engineers or computer science.
That's a great point, actually. So OpenAI actually has a lot of people from different backgrounds. Physics, neuroscience are some of them. And there are also many programs. For example, the fellows program at OpenAI is still ongoing, and the target is especially to find people from different domains that don't have CS or AI backgrounds, and just to train them to become research scientists. So that kind of effort is definitely happening, and as these awesome people just keep joining the company, the diversity of the task force is increasing. So yeah, I mean, I also don't come from an AI background for one, and we also have mechanical engineers, for example, and yeah, we're really looking for people with strong skills, and then they can join the team and build something awesome while learning on the job as well.
Thank you.
I have a few more if you are still available. Okay. Mm-hmm. One of them is relating to the general RL problem, and that's when the people are starting to getting interested with RL and getting hyped about it, but then when actually if you look at industry or job offerings, you can clearly see it's not like really in the solid states, such as like maybe vision, computer vision, or NLP, or other things like recommendation systems. So what do you recommend, like people or researchers maybe, or engineers that already worked and now maybe transitioning to a researcher position or something like that? So do you think like RL is a solid, do you think maybe now or in the near future RL will be way to go for them, or do you think they also should keep some other background to fall, like a computer vision or something?
That really depends, actually. Like I'm also biased because I work on robotics and you have to use RL, but also like in other domains, there is this trend. Yeah, like language models are really popular, transformers are out there. Things are happening, and mostly happening because like these new architectures let you use a lot more with data, and there's a lot of data out there that you can use for supervised training. But for RL, it's a little trickier. But at the end of the day, it's really very useful for a very broad set of things. Like if you have a language model, and if you want to make something useful for humans with it, you're going to have to use RL at the end of the day. You're going to have to fine-tune the model for something that humans care about. So I think that's still going to be there all the time. So I mean, yeah, but it's very interesting. Like I wouldn't be able to compare it with computer vision, for example. Like it's very hard to say any of these problems are solved at this point. It's kind of a good time to be in AI.
Yeah. Maybe one of the last questions from me, and I will just read from one of the YouTubes, and after this. Okay, I think these are mostly completed. And from the chat, I think I will just read them. If they are Turkish, I will just read them in the Turkish or English, depending. One of our viewers asked about finance in the RL. So do you maybe, I don't know if it's maybe not your domain, but do you have an idea about like using finance with the reinforcement learning, finance, so like time series data and things like that?
I'm afraid I'm actually not an expert at all in finance. Sorry.
Okay. No problem. Bir tane Türkçe sorumuz var. Artık onu Türkçe okuyayım. ADR fikriyle ilgili bir soru gelmiş. Bunu yani ilham veren nereden geldiğini soruyor. Diğer sanırım elle yapılan diğer yöntemlerden bahsediyor. Eğitim süresinde uzun olduğunu düşünürsek bunların yani sonuçlarını görene kadar yılmadan nasıl gidebildiğinizi veya bu fikrin yani gidilebilir bir alanda olduğunu nasıl anladığınız tarzında bir soru sormuş. ADR ile ilgili, Auto Domain Randomization.
I'll just repeat that in English and then answer. So the question is, how do we come up with the idea of ADR, and how do we basically convince ourselves that it was an interesting problem to keep working on? Does that cover it?
Yes.
Yeah, so that is actually a great point, and I'm going to go back to basically this very early results to answer that question. So the learning dexterity problem, as you can see, is just a stepping stone towards Rubik's Cube. And I think so I wasn't actually there at OpenAI at the time, but I just got the context that it was a stepping stone and it got enough signals to keep us moving in that direction. So when this work was done, ADR wasn't there. It was achieved with domain randomization, but there's this clear trend here. Okay, so we can use purely vision. We can flip this cube reliably for 50 times using this robot hand. So all we need to do now is to teach it a new skill, which is to flip a face of a cube. And in this case, not only an RL problem gets harder, but also the hardware problem gets harder. Like your cube actually has to be modeled pretty well in simulation, and you have to do everything else. But I would say, like, if it wasn't for the 2018 result, we wouldn't have continued on to the Rubik cube. So it's kind of speaking to the importance of breaking down things into milestones when possible.
Thank you for that answer. I hope it answers the question from Yahya. And one of the other questions is in English, and it asks about what's the advantage of using discrete action space instead of the continuous action space on the fingers?
Yeah, that is actually a great question as well. Let me go back there. So the thing is, PPO is actually able to deal with both continuous and discrete action spaces. So you can totally do that, use continuous control. But in our case, the discrete action space, actually both in vision and manipulation, was much more accurate. So it was just a practical decision that, okay, like we only care about moving this particular finger joint in an action space that is, let's say, that has 120-degree range. So why not discretize the space into 11 bins? It's more than enough precision that we care about. So it's really about simplifying the problem for getting more accurate and fast results, I would say. But you could, in practice, you could do both.
That's also really helpful to understand. The last question we had is from Ertan, and he asks about the technical question regarding to the algorithm and how it works. And the question is basically this: what was the lagging point? Was it the reaction time between fingers and the arm, or was it the processing the camera information and just trying to move the fingers, which was the most time-consuming part in the real world? I think what he's asking.
Yeah, that is a great question. I spent many months on this problem. So the answer really is everything, but you have to build enough instrumentation to let you debug the system. At the end of the day, this is really like a distributed software system, only more complex. So what you do here is, for example, vision latency is one factor that hurts a lot. In our case, robot dynamics also one thing that hurt a lot. But so that's actually an argument for, I'll go in steps. So for the vision one, we added instrumentation to see, okay, once we sample the image from the 3 RGB cameras, how fast do they get into the policy? If the answer is something above 5 milliseconds, it's usually a problem. So you have to make sure that latency remains consistent. There's something you can do about this, and we did that. So you can randomize latencies in your policy as well. So once you sample an action, for example, you can randomize that latency for the time you wait until you apply that action to your environment. And this is also a good thing about sim training. So we did that as well. So that helps with latency. The system knows that it's not going to expect to deterministically see the effect of the action 1 nanosecond later on the system. It is able to tolerate some latency, and you know that latency toleration as well. So in our case, our step time was 80 milliseconds on the real system. So it's not the worst in terms of real-time requirements, but also not the best. And we were not using a real-time operating system. It's just using plain old Linux, and that's why you have to cut some corners when trying to make sure everything is working well. So that's one factor. And the second thing I'm going to talk about is the dynamics of the hand, as I said. That was also very important. Like the hand is very complicated, 24 degrees of freedom, basically, I said. And anything can break at any point, and you may not be able to detect it. So that was a huge problem for us. Like if the hand is in a degraded state, nothing is working, but it takes us a while to find out that the hand is actually broken. And that was the thing. Like we were actually constantly repairing the hands and making sure that they were consistent. And we had several of those by the end of the project. But yeah, so when something breaks, you have to suspect everything. So we ended up actually building the super nice monitoring system so we can know that everything is working and then actually attempt to deploy policies so that our experiments are actually reliable.
That's a really great answer for this. I hope he listens to the answer. And I think the questions are kind of okay at the moment. And I just had one last thing from my side, and that was the maybe a theoretical, not a theoretical question, but what do you kind of suggest for more of a younger audience that maybe starting RL or just started the RL? So which are like areas or open problems that you think they should maybe focus on? There are a lot of questions to be like solved, but I just wanted to learn what's your idea, and then maybe you can just tell what's your recommendations, and we will just after that complete the stream.
Yeah, I mean, there are really great resources out there. I mean, I also went over these when I started OpenAI. There's this spinning up introduction that can be found on the OpenAI's website. Just has a very great overview of the field in its form today. So yeah, there are really a lot of resources out there. So I would really recommend just go and solve some things by themselves, just practice a little bit. In terms of interesting problems in RL, there's really a lot. I mean, it's impossible to not be biased, I guess, in that case. Some of the newer contrastive methods are pretty interesting to me. So I'm going to mention those, I guess. But yeah, I mean, OpenAI Gym, again, it was a great asset for me to get started on. There's the safety approach. So there's the safety gym now as well. So that's also another important thing, I think, for my interest, because like when you're doing something like this, you don't always care about the RL reward, for example. You also care about the physical control policy being reasonable for a physical system. Like actually one problem that we see all the time is this bang control problem. Like your neural network doesn't care that you're working with a physical system. It will ask you to apply the maximum action and then the minimum action repeatedly over and over. And it's terrible for a physical system. You want a smooth trajectory. And you cannot get that from a neural network unless you actually incentivize for it explicitly. So there are these methods like constraint PPO, for example, that you can use a cost and a reward, and it will adaptively maximize your reward while then minimizing your cost. So you can impose some priors to the network to be more compatible with physical hardware. So yeah, some biased answers to that question there.
Okay. Thank you for the answer. I think we will just stop there and won't thank you for more time. And it was wonderful like a presentation that I learned a lot. I will have to check again because I didn't see full of all the answers or all the questions. And I hope everyone enjoyed it and can watch it later on if you couldn't keep up the live stream. And thank you for joining us today. It was really nice for us also. Yeah, that's basically
sure.
from us.
Thank you.
Thank you.